that doesn't have a lot of pores, or that the pores aren't very well connected, you need more pressure to move the water through. If this is like gravel or big rocks, the water will move through much easier. You need less pressure. And so there's a law called Darcy's law, which basically incorporates everything I've just said. So the mass has to be conserved, the energy has to be conserved, and there's this resistance to flow due to what the material is like. And that Darcy's law is basically that governs everything that we do with the groundwater when we study groundwater. And I said this at the beginning, but to predict and understand groundwater and surface water interactions, we typically need a model. And there are a couple of reasons for this, but first whenever I'm kind of confronted with a new term, I like to go to the dictionary sometimes. I find it useful. Even for something, I've been doing groundwater modeling for 15 years, and I thought, I should look at the dictionary. What does it actually say about a model? And it's a simplified description, often mathematical, of some kind of system or process that's assisted to make calculations or, very importantly, predictions. And so if we want to understand, if we're going to change something in the environment, the groundwater environment, and we want to see what is that going to do to some kind of response we care about, whether that's a stream, a lake level, or something else, a model is a very effective way to do this. And some people think that models are overused, but I would argue that they're kind of everywhere. If you've ever been in a car, or an airplane, or sat on a chair, or gone across a bridge, almost certainly at some point in the process there was a model used in the design of that. Now that model may have just been some calculations on a piece of paper, it may have been some really sophisticated computer model, but the only way that we can test things and sort of make predictions about something is using a model. And so I already kind of explained this conservation of mass and conservation of energy, and so basically what I like to say is that that's how we honor the physical and chemical laws. Like, we know what these laws are, so we need to make a model that honors those, that represents those correctly. But we also have to honor the specific site, the actual data we have about a specific place on the Earth. And we do that by understanding the connections with the hydrologic cycle, and then by calibration. And this is actually my specialty. So of course I had to add a little sentence saying that this is totally vital. But it is. I speak the truth. So calibration, basically what this means is you need to make a model that not only is correct in the sense that it honors the physics and the chemistry and whatever, but that it can predict things that we already know. So that we can make the model, and if we run a simulation of current conditions, the results of that match what we actually know, what's actually going on now. Then we can start to think about making predictions of future changes. But first we have to make sure that it's actually representative of the system as we know it now. And of course, that will never be totally certain and perfect, so rather than pretending that it's perfect, or waving our hands and saying we don't know anything, we spend a lot of time trying to characterize how confident we are in that model for different purposes. And so I think models have a few different values. First of all, as a conceptual model, it serves as a cohesive framework to consolidate and interpret data. So we get all this information, and I'll show you some of the information we have for the Bad River watershed now, but we need to sort of make a cohesive picture out of this, and it helps us understand what the system is really like. And of course, what we're often after is a platform where we can test scenarios, see what the response is, and then add some kind of a margin of safety. So that's where the uncertainty part comes in. We make a prediction, but we also try to be conservative with that prediction. So that we try not to conclude that something is safe if it's really dangerous, right? So and by using the model, we have the ability to add that kind of range to our output. And then in decision making, models are a great feedback mechanism to revise what we understand about a site and to guide the next steps. And so this is really important for for the model that I'm going to talk about a little bit in a minute, but I'm going to save that thought. So you just got a picture inside of my brain, and I'm sorry for that. All right. So there are a few choices that you have to make about what kind of model you're going to create. And one of the things that is really important is to understand that the kind of model that you make and the way that you use the data is really a function of what question you're actually trying to answer. So I would say that the results of all models are contingent on the conceptual model, so kind of how you're looking at the system, which particular technique you choose to use, and all the other choices about how you're going to use data. This may seem a little bit obscure, but if you want to have that margin of safety with a model, that may be at odds with another model. And I'll give you an example of this that I've seen before. So say that you have, like you're interested in how much water is flowing into a line, right? And you're interested in that because you want to know if there's more water that will dilute some kind of chemical. And so the more water that comes in, the safer it would be. But to have a margin of safety, we would say, well, when we have a choice about choices of how we make the model, we'll make it so it lets in less water. So that what answer we get is the worst case scenario, right? So one choice we might make to do that is to not allow much water to come in from the surface. So we assume that there's not much water coming in from the surface, and so any water that gets into the mine is from the surrounding area. Less water, higher concentration, worse outcome, right? If it passes that test and it's still safe, then we can be confident that the mine could go forward. So in that particular example. But what if we had a different question, which was, are wetlands going to dry up? So now we have the opposite case. We want to see a case where lots of water, the margin of safety is to allow plenty of water to go into the mine so that it's actually drying out the wetlands at the surface. But in order to have a margin of safety on the first model, we cut off that surface. So if we use the same model, we're actually making the opposite conclusion. So that was a whole lot of spaghetti. The point is, to have a margin of safety for one question, it may actually contradict the margin of safety for another question. So one model is not necessarily, or one kind of setup of a model is not necessarily appropriate for every question you want to answer. And so when we have to choose a model, there's a whole range of choices that we can make from the simplest to the most complex. And the tools that we use at the simplest are just calculations, back of the envelope calculations. And for some questions, that's just fine. Like, we're a little more sophisticated than the back of the envelope, but basically, that's true. There's a tool called an analytic element, which is sort of in between, and we often use as a screening model. I'll show that in a few minutes. Or we can go to fully numerical, and these are just some names of those. But in any case, when you're making a model, especially if there's any chance that there's any controversy around the topic, looking at the track record of how that type of model has been used in the past, and its kind of legal history, like has it been used in court cases in the past, is an important thing to consider. And so we've talked a lot about different aspects of the model. We've got that resistance to flow thing. We've got the connections to the surface water system and to the hydrologic cycle. So all of these things we call parameters. So those are the things that are site-specific and control how the model reflects a specific site in the landscape. But we can't measure a lot of these things directly. And this is part of the reason we're using the model in the first place. It's very difficult to measure these things the same way that we can measure, say, flow in a river. So we have to infer them. So we have to take the data, run the model, and then see how that matches reality and kind of adjust. And this isn't unique. It's a little bit like looking through a clouded glass. So both of these look about the same. if you're looking through this cloudy glass, but the reality is actually a little bit different. But how do we do this? So, okay, say this is like a watershed. We've got a little river going through it, and we have a few wells, and at those wells we know the water level. We've got a couple stream gauges, and so we know also the flow through those streams. We can create a model, and so it's going to be, some simplified version of reality. Probably in reality it's even simpler. We have to make some assumptions in order to make it possible to do. And now we have these are contours of the water surface, of the water table surface. So going from high to low, that's what the blue line here is. That's what we've measured. And so we use a set of parameters, and we run the model, and we get this. We get something that's, it's kind of the right planet. It has similar behavior, but it doesn't match all that well. But the parameters can act kind of like little dials here. And you twist those dials around until you get your data to match what the model is telling you. And if there were just two of those, that would be great, because you could just change the model a few times and run it. But in reality, it's a little bit more like mixing a big rock concert. You've got dials all over the place for various things. And the more complex the model is, the more parameters there are. So we can't really rely on just trial and error, just trying each node and seeing what happens. Luckily, there is a systematic approach to doing this. Also, we know that every one of these parameters has some uncertainty. We never know it perfectly. And so any prediction we make from the model reflects a little bit of that uncertainty. So we have to carry that all the way through. And there's a famous statistician from here in Wisconsin that said essentially all models are wrong, but some are useful. And what this really means is that we don't expect to perfectly reproduce the measurements that we have. No model is perfect. So we acknowledge that it's not perfect. And we also know that the measurements are not perfect. But luckily we have these robust statistical techniques that allow us to consider these sources of uncertainty and be honest about how realistic they are.